Hello, and welcome to the third in a series of 6 films about the standard level equilibrium topic. In this film we're going to be talking about Le Chatelier's principle, and hopefully by the end of it you will know what it is that Le Chatelier's principle tells us about equilibrium systems, and also you'll understand how it is that equilibrium systems can minimize the changes imposed upon them, which might sound a little bit obscure at the moment, so let's have a look at what we mean. So Le Chatelier's principle, the reason I haven't put this in print on the slide is because it's not a law that you have to be able to state in an exam. You don't have to regurgitate this principle, but you do need to know what it means. What Le Chatelier's principle says is that for any closed system at equilibrium, so that's a system where things can't get in and out, the system will respond in such a way as to minimize any change that we impose on the system. So in other words, you could think of this as basically being a statement about the system kind of being quite stubborn. So if I make some kind of change to the system, if I, for example, heat it up, then the system will try and do the opposite. It will try and cool itself down so that the change I made is minimized. Now let's have a look at how that might actually happen in a moment, but what we're going to try and do, although we don't have to be able to remember the principle, we do have to be able to explain things in terms of it. So in an attempt to try and make sure that these explanations are always clear, it might be a good idea to try and stick to a routine every time you try and explain something. So this is the routine I'm going to follow in this film. Anytime I'm trying to explain what's going on, I'm going to try and say what the system will do in response to the change. This will be something about the conditions. How the system will achieve it, and that will be something about the forward or backward reaction, and why that change that the system undergoes will bring about the change that it's hoping to achieve. Okay, and there'll be a bit more about that to follow. Okay, so bear in mind that we are trying to stick to this routine, and if you want to make sure that your answers are clear in an exam, it might be a good idea to have a similar routine yourself. Okay, let's start off by looking at how a system might oppose changes in temperature. Now, what this is driving at is, as I said before, if I try and heat a system up, it will try and cool itself down. If I try and cool it down, it will try and heat itself up to minimize the change. Okay. Now, when we're considering how systems might do that, we need to know whether they're exothermic or endothermic, because exothermic reactions get hot, endothermic reactions get cold. And anytime I look at an equation for a reaction, I'm looking for some information about whether it's exothermic or endothermic if I'm going to be able to discuss what a change in temperature will bring about to an equilibrium system. So often we'll be told something about the enthalpy change for a process. And by default, this refers to the forward reaction. Now here we've got a negative enthalpy change, and we hopefully remember that that means this reaction is exothermic. As I've just said, this means that it's exothermic in the forward direction. That means that in the reverse direction it must be endothermic, because it's simply the reverse process. Now, bearing these things in mind, and bearing in mind the routine that we've just discussed, if I raise the temperature, what will the system try and do? It will try and lower the temperature. How will it try and lower the temperature? It will favour the backward reaction. It's not very well written, but hopefully you can tell what it's saying. It will favour the backward reaction. Why will it favour the backward reaction? Because the backward reaction is endothermic. Okay, so if I was asked to explain what effect an increase in temperature will have on the position of this equilibrium, I'd say that the position of equilibrium would move left, because as I raise the temperature, the system tries to lower it by favouring the backward reaction because it's an endothermic reaction. Okay, I could say the opposite about lowering temperature. Okay, if I lower the temperature, the system will try to increase it. Okay, so my routine is, I've been told what effect will lowering the temperature have. The system will try to increase the temperature. How will it increase the temperature? It will favour the forward reaction. Why does it favour the forward reaction? Because it's an exothermic process, and that will raise the temperature. Okay, so obviously I could have had an endothermic reaction if that had been a positive value, and then raising the temperature would have the opposite effect on the position of equilibrium. But hopefully you can see there how it is that the system is going to bring about changes in the conditions by moving either left or right, depending on the conditions that I try, or the changes in conditions that I try and impose on the system. Now, if we're going to be looking at changes in concentration or pressure, by the way, I've grouped these together because they're kind of the same thing, really. Concentration refers to how many moles of particles we've got per unit volume, and pressure is related to how many particles we've got per unit volume. Okay, so they're quite similar things. And if we're talking about things that are dissolved in others, then we'll be talking about their concentration. If we're talking about reactions that have gases in them, then we'll be talking about their pressures rather than their concentrations. But they're equivalent concepts, really. Now, if I remove a product or a reactant, okay, let's go for the product, okay, and say, what will the system try and do? It will try and replace the product, because remember, it's trying to do the opposite of what I'm imposing on it. So it will have to replace the product. How will it replace the product? Well, the product is here, so it would have to favour the forward reaction. Why would it have to favour the forward reaction? Because this produces C, which is our product. Okay, so again, I'm following the routine here. If we removed some C, what effect would it have on this equilibrium? Well, it would move the equilibrium to the right. Why would it do that? Because the system is trying to replace the product by favouring the forward reaction, because that's the reaction that produces C. I'm not going to keep writing all of these down, okay, because it becomes repetitive, but repetition, I suppose, is no bad thing in some ways, but we want to make the film fairly short. If I added a product or reactant, let's say a reactant, okay, if I add a reactant, what's the system going to try and do? It's going to try and remove it. How's it going to remove a reactant? It would have to favour the forward reaction. Why would it favour the forward reaction? Because the forward reaction uses up the reactants. Okay, so that's what systems will do if we add or remove products or reactants. Now that's different to overall changes in concentration or pressure. Okay, so here, usually by changing the volume of a container that a system is in, we might change the concentration of everything at once, or the pressure of everything at once. Now, what's a system going to do about this? Well, let's consider this equilibrium system we've seen quite a lot of up until now. We've got A and B turning into C, and C potentially turning back into A and B. Now we could imagine the two extremes here. We could say the position of equilibrium lies entirely to the left, where we've just got A and B in our container. Or the position of equilibrium could lie entirely to the right, where we've just got C in our container. Now I've been careful here in these two diagrams to show the correct proportions of particles. Okay, if I had one of each of A and B here, then I would produce one of C for every one A and B, as shown by our mole ratio in our equation here. We can see that 1A and 1B turns into 1C. Okay, now hopefully it doesn't take too much imagination to see that if we were in this situation, in this container, and these things were all gases, that the pressure would be higher inside the container if the position of equilibrium were to the left, and it would be lower inside the container if the position of equilibrium were to the right, because there are fewer moles of gas on the right hand side of the equation, so there'll be fewer particles in the box if the position of equilibrium is to the right. So we've got a clue here as to how a system might counteract an overall change in pressure. If I increase the pressure, it would move to the side that has a lower pressure. If I decrease the pressure, so I made the volume of the box bigger, say, then it would move to the side that increases the pressure, the side with most moles of gas. So, if we look here at what might happen, if there's an overall change in concentration or pressure, let's say I decrease the volume of my container, what is the system going to try and do? Well, it can't change the size of the container, but what's happened when I decreased the volume? Well, I increased the pressure. So what's the system going to try and do? It's going to try and lower the pressure. How's it going to lower the pressure? It's going to favour the forward reaction. Why is it going to favour the forward reaction? Because there are fewer moles of gas on the right hand side. Okay? Similarly, but again, I'm not going to write this down because hopefully you're getting the hang of it by now. If we increase the volume, that means the pressure is going to fall. What's the system going to try and do? It's going to try and increase the pressure. How is it going to do that? It's going to favour the backward reaction. Why is it going to favour the backward reaction? Because the backward reaction produces more moles of gas. Okay, final thing to consider is the other change in conditions that we might have. We might be introducing a catalyst. Now, what might this do to the forward and backward reactions? Well, if I add a catalyst, what we hopefully remember from the energetics topic is that the catalyst provides an alternative reaction pathway. And this reaction pathway has a lower activation energy. Now, on this diagram, we've got shown the activation energies for the forward reaction, right? But I could equally well show the activation energies for the backward reaction, right? That would be without the catalyst, and this would be, where are we? That would be with the catalyst. And so we can see that whether we're going forwards or backwards, the activation energy is smaller in the presence of the catalyst. Okay, so the blue lines are for the backward reaction. And because the catalyst speeds up both the forward and the backward reactions, adding a catalyst has no effect on the position of equilibrium. Okay, so if we're asked to explain why, okay, if we add a catalyst, the system, I suppose, what does it try and do? It's a bit difficult to say in this example, but how does it do it? Well, it doesn't do anything. Why does it not do anything? Because the forward and backward reactions speed up by the same amount. Okay, so what we've tried to do there in explaining how equilibrium systems can minimize the changes imposed on them is we've tried to follow this routine that brings in Le Chatelier's, or that uses Le Chatelier's principle to explain things. Remember, you don't have to remember Le Chatelier's principle, but you do have to have in mind what it states, otherwise you can't follow this routine. Okay, if there's anything in this film that is a little bit confusing, or anything that you want to ask about, or anything that perhaps you want to comment on, please feel free to come and see me or post a comment on YouTube.